Section 4.6 is counting. You only thought you knew how to count. In many probability problems, the big obstacle is finding the total number of outcomes in your event or in your sample space. And here we're going to look at several different methods for finding these numbers without directly listing or enumerating those possibilities. The fundamental counting rule says for a sequence of two events in which the first event can occur m ways and the second event can occur n ways, the events together can occur a total of m times n ways. I've kind of been doing that with you without explicitly telling you that's what I've been doing. We've been multiplying the probabilities together. Now for just counting, we're going to just multiply the number of options together. A Social Security number consists of 9 digits in a particular order, and repetition of digits is allowed. If randomly selecting digits for one Social Security number, what is the probability that you get a Social Security number of the president? Social Security numbers have 1, 2, 3 numbers, then 2 numbers, then 1, 2, 3, 4. The probability of guessing the president's Social Security number, assuming that he has only one, there's only one element in our event, and that is the president's Social Security number. The problem comes in with the number of elements in our sample space. Your sample space is every possible Social Security number there is. Counting those would be an arduous task. But using this counting rule, all I got to do is come up with the number of ways that I can get the first number times the number of ways that I can get the second number times the number of ways that I can get the third number, so forth and so on. And that would multiply all those numbers together, and that gives me all the possible Social Security numbers. So how many choices do I have for digits of this first number in our Social Security number? 10. There's actually 10 because we go 0 through 9. So that's 10 digits. You're allowed to repeat numbers on Social Security numbers. So how many choices will we have for the next number? And the next? And the next? There's actually 10 choices for all of these. And if only one of them is the president's number, then the probability of guessing the president's number, Social Security number, is going to be 1 out of 10 raised to the what power? 9th? Or that's 1 with 9 zeros. So that's 1 out of 1 billion. I think the probability of guessing the president's Social Security number is way lower than the probability of winning the lottery. I'm making up a problem now. The probability of randomly guessing somebody's phone number. Well, first of all, in America, we have a 3-digit area code, we have a 3-digit prefix, and then we have 4 numbers. In your area code, it cannot begin with 0 or 1. So how many choices of numbers do you have there? 8. So we have 8 numbers we could pick here. And the next digit, there's no restriction, so we could have 10 numbers here. Same thing here. In the prefix, once again, you cannot start with a 0 or a 1. So there's 8 again. And then we can have any numbers we want in the following numbers. So the number of phone numbers available is going to be 64, and then 1, 2, 3, 4, 5, 6, 7, 8 zeros. So there's a total of 6,400,000,000 phone numbers in the United States. Once we get over 6 billion phone numbers, we're going to have to add another digit to the phone number system. Lots of different ways to come up with phone numbers. Have y'all seen the exclamation point on calculators? On your calculator, it's a little hidden if you have the graphing calculator like this. If you hit math and then go over to probability, you see right there the little exclamation point? That's called a factorial. In order to use the factorial, first you have to put a number on your home screen, then you hit math, probability, and 4 will get you the factorial. Now what this is it's 4 times 3 times 2 times 1. The factorial only works with integers. You can only use it with integers. And what it does is it starts with whatever integer you have here, and then it multiplies each number decreasing by 1 each time. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. These numbers get really big really fast. 0 factorial by definition is 1. The factorial rule says the number of different permutations or order counts of n different items can be arranged when all n of them are selected. This factorial rule reflects the fact that the first item may be selected in n different ways, the second item may be selected in n minus 1 ways, and so on. So if I let n be 6, this is n times 5 is n minus 1, 4 is n minus 2, 3 is n minus 3, 2 is n minus 4, until you get down to 1. You just keep going. Let's look at an example. You need to arrange 7 of your favorite books along a small shelf. How many different ways can you arrange the books, assuming that the order of the books makes no difference to you? So you have a shelf and you have 7 books, your 7 favorite books. How many choices do you have for the placement or what book goes in the first position? 7. And how many choices do you have for the next book? You see how this works? 4, 3, 2, 1. So if you want to know the number of different ways you can arrange the book on your shelf, all you got to do is find 7 factorial, and that's 5040. There's 5040 different ways you can arrange those books on your shelf. So we're counting the number of ways that we can do something. The permutations rule, when all the items are different. The requirements are that you have n different items available, and we're going to select R of those n items without replacement. We consider the rearrangements of the same items to be different, blah, blah, blah. So ABC is different from CBA. Even though it uses the same letters, it's actually a different arrangements. So we can use this permutations when we're trying to come up with passwords, wanting to know what the passwords are. With permutation, order matters. That's the thing to keep straight. Let me draw an example problem here. How many different 4-letter passwords is it possible to create? If order matters, because ABCD changes is a different password from EFGH. And there's no repeating. There's no repeating allowed. So I've got 4-letter passwords. How many choices do I have for my first letter? There's 26 letters in the alphabet, guys. There's 26 choices for that first letter. How many for the second letter? How many for the next letter? And the next? This is the same thing as 26 permuted by 4, 26p4. Let's go to our calculator to see how this works. If I do 26 times 25 times 24 times 23, I end up with 358,800. But if I do 26, math, probability, go to the p here, that's number 2, 4, I end up with the same number. That's because I have 26 items to choose from, and I'm choosing 4 at a time, and the order of those items mattered. So this is going to be 358,800. You don't have to memorize this formula. We're going to use our calculator. And how I got to this on my calculator was I hit 26 on the home screen, and then I hit math, go over to probability, and then down to number 2, and then hit enter. Order matters with permutation. The next thing we're going to look at is combinations. And with combinations, order doesn't matter. With combinations, we're still looking at n different items, and they're selected R at a time without replacement. But now order doesn't matter. So for example, if I had the letters A, B, C, D, and I wanted to choose 3 letters at a time, I could come up with A, B, C, A, C, B, C, A, B, C, B, A. I got B, A, C, and B, C, A. So all the different ways to combine A, B, C. I left D out. Now I'm going to look at A, B, D. I'm going to leave C out. Well, I could also combine that using A, D, B, B, A, D, B, D, A, D, A, B, and D, B, A. I left C out. Now I'm going to leave B out, A, C, D. I could also have A, D, C, A, C, A, D, C, D, A, D, A, C, and D, C, A. Now I'm going to leave the A out and have B, C, D, B, D, C, C, B, D, C, D, B, D, C, B, D, C, D, B, C. What I've done here, I've shown you the difference between ABC, I've got 4 letters, choosing 3 at a time. When I look at combinations, all of these are the same. There's only 4 different combinations I can come up with. However, there are 24 permutations. So if I've got these 4 letters, A, B, C, D, and I choose 3 at a time, if I consider that order matters, I have 24 different permutations of these 4 letters chosen 3 at a time. If I don't think that order matters, then I only have 4 combinations of those 4 letters chosen 3 at a time. Here's a situation where that might apply. Consider a club, and we're going to have to elect officers. There's 12 people in our club. If we're electing officers and we're going to cast votes, popularity contest, the person with the most votes becomes president, second most votes is the vice president, third most votes is the secretary. Does order matter there if you come in first, second, or third? So the number of ways that I can come up with officers is actually going to be 12p3, 12 permuted 3 ways. So there's 1,320 different ways that I could come up with officers. But if I were just going to select people to serve on a committee, and I was going to select 3 people to serve on a committee, would it matter if you're selected first, second, or third? You're either on the committee or you're not, right? So order doesn't matter. So there we would look at 12C3, and this would be 12 combined 3 different ways, or 3 at a time, and that would be 220. So there's 220 different combinations that I could come up with for people to serve on a committee, because you're either on or you're off. The order doesn't matter. Now there's one more permutation rule, and that is whenever you have things that repeat, when some items are identical to others. This is another formula. Using this formula for permutations, in how many distinct ways can the letters of the word Mississippi be arranged? In factorial, n is the number of letters in Mississippi. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N is equal to 11. Then these numbers down here are all the ones that are repeating. How many I's are there? There's 4 I's. How many S's are there? 4 S's. And how many P's are there? 2. So the formula, or the number of ways we can arrange the letters here, would be 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. And when you put this in your calculator, you want to make sure that you use parentheses carefully. This is 11 factorial divided by, open parentheses, 4 factorial, 4 factorial, and 2 factorial. And we come up with 34,650. All right, the last 2 example problems from section 4.6. We have this question that says, a history pop quiz asks students to arrange the following presidents in chronological order. We have Hayes, we have Taft, we have Polk, Taylor, Grant, and Pierce. How many presidents are these? 1, 2, 3, 4, 5, 6. So the probability, we're asked to find the probability of guessing correctly on the order. First of all, there's only one correct order. So the number of ways that I can come up with the correct order is going to be equal to 1. Now, the number of possible combinations, all possible, or let's say all possible arrangements, is going to be equal to what? 6 factorial, isn't it? Now here's the reason why I say it's 6 factorial. I've got to arrange the presidents in order. How many choices do I have for the presidents that I put in the first position? 6. I have 6 to choose from. So now I've placed a president. I don't care which one it is. Then I've now to put in the second position, how many choices do I have? And then 3, 2, 1. And when we multiply these numbers together, by definition, this is 6 factorial, right? Remember when we talked about the definition of factorial. So the probability of guessing and getting these correct is going to be equal to 1 divided by 6 factorial. So we go to our calculator and we've got to figure out what 6 factorial is. I need a number for it. So we hit 6, and to get to the factorial, remember we go to math, probability, and number 4 right here is the factorial button, and we get 720. So the probability of guessing and getting this correct is 1 out of 720. It says in the Pennsylvania Match 6 Lotto, winning the jackpot requires you select 6 different numbers from 1 to 49. The winning numbers may be drawn in any order. Find the probability of winning if one ticket is purchased. So the number of elements in our event here, which would be a win, would be 1. There's only one way that you can choose the same 6 numbers if order doesn't matter. Now, the number of elements in your sample space is going to be all possible 6 number combinations with the digits 1 through 49. So we have 49 digits to choose from, and since the order does not matter, we're going to use combinations, and we're combining them 6 at a time. So this is going to be using the combinations here. So the probability of winning is going to be equal to 1 divided by 49, choose 6. So we go to our calculator and we find out what 49 combined 6 ways is equal to. So we go down to probability. Number 3 here is combination, and we're choosing 6 at a time. So that's going to be 13,983,816. So 1 out of almost 14 million. The odds of winning the lottery are not great. That's why it's not a good, sound investment strategy for retirement.